Alright, I'm going to start this video out, as I always do, with a look at Chuck Penson's excellent book, Heathkit Test Equipment Products. Just flipping to the section on analog VOMs, multimeters, and voltmeters. I've visited this chapter many times before for other videos I've done. And most recently I did a video on the IM-5238 FET Multimeter. But now I'm going to talk about the IM-5238 AC voltmeter. This meter was introduced in 1976 and was discontinued sometime in 1981. It sold for just about $100. It was the solid-state replacement for the tube-type IM-38, which on the chapter on VTVMs, which does include the IM-38 as the AC VTVM only. So, vacuum tube voltmeter for sure, but AC only. And that in turn is a later version of the IM-21. Anyway, so good if you only need to check AC volts. In styling, the IM-5238 was a complete departure from the tube-type versions and featured push-button selection and functions. The basic ranges are mostly the same as in the IM-38, with an improvement in the decibel ranges. 12 full-scale ranges measure from 0.01 to 300 volts RMS. The dB ranges have been shifted to -70 to +40 dB in 12 ranges with variable offset. Input impedance is 10 megaohms. Frequency response goes from 10 Hz to 1 megahertz. After this product was discontinued in 1981, there was no further AC voltmeter product that Heathkit produced. Alright, here's the artifact as received from eBay. I did a very perfunctory power-up and just put some volts into it from a signal generator and also from the AC line via my Variac, and it seemed to be basically functional. Looks like it could use a calibration, but otherwise seems to be in pretty good shape. The only thing that I really anticipate I'll have to do to this to bring it up to the standards of my collection is to recap it. After all, this unit is about 50 years old, and I don't anticipate that the electrolytics, at least, will be in very great shape, although they're probably functional. If they weren't, the unit wouldn't have worked as well as it did in my initial tests. Let's just take a look at the meter face and the front panel. So we have the input with plus and minus binding jacks, but since it's AC, it does seem kind of odd that they used red and black on here. Having said that, the black one is connected to circuit ground and also to chassis ground, so it is not an isolated input. This side is definitely connected to earth ground, and that's not really avoidable unless you cut a wire inside. The power light, the function selectors, one of them is actually the power switch. This is the one you push if you want to read volts. This is the one you push if you want the meter to be in decibel mode. There is a 12 position rotary range switch. It starts at the counterclockwise position with 1 millivolt full scale, 3 millivolts, 10, 30, 100, 300 millivolts, and then continuing with 1 volt, 3 volts, 10 volts, 30 volts, 100 volts, and 300 volts full scale. If we're in the decibel mode, it's -70, -60, -50, -40, -30, -20, -10, 0, +10, +20, +30, and +40. And there's also a offset adjust for the decibel mode, and that's this concentric red knob. If it's left in its full counterclockwise position, that's the calibrated position. This allows you to set the meter up to get accurate readings if they're not exactly what the scale markings or the range markings indicate. There's a procedure in the manual for using this so that you have it set correctly when you're sort of off the reservation as far as the fixed ranges go. The meter has this decibel range here, and then it has the decibel range -20 to +10 on here. Then there are the volts scales, 0 to 10 and 0 to 3.2, which is interesting. You'd think from the circuit design and the ranges that the 3 on here would be precisely aligned with the 10, but for whatever reason they're not. I'm presuming there's some small resistance compromises or something that make it skewed slightly on the 3 scales. There's also a mirror on here so you can avoid parallax issues for taking accurate readings. Here's the rear panel. There are 5 jacks on the back, but they don't have the binding posts. They're just simple banana jacks. And these are for the outputs that are provided by the internal circuitry for connecting up to external equipment. For example, another meter, a chart recorder, or something like that. As the pictorial here shows, these 2 jacks are volts out, so it's a voltage output that's proportional to what's being displayed on the meter. As I recall, it was 1 volt full scale. I'll verify that later when I talk about the circuit theory. Then the bottom 2 jacks are the AC output. This is right off of the front end amplifiers. And again, I think this is about 1 volt full scale, or you'd get 1 volt AC on here when the meter's at full scale, whatever the range might be. And then finally the decibel output. It takes the DC output and converts it to a logarithmic version of itself, which is roughly 0 to 3 volts after the conversion, and that's applied between these 2 or these 2. These are electrically commoned. And there's a line voltage selector switch here. And of course the power cord coming in. That's all there is. It's a pretty simple device. Alright, I have the cover off. Let's take a look at the inside. 1 printed circuit board, single-sided. A fairly simple range switch. If you've seen my video on the similar looking IM-5238 FET Multimeter, it has a much more complicated circuit board and a very complicated multi-ganged selector switch. This one really has the very simple single gang wafer here for selecting the 12 ranges, and it's a simple single common 12 position selector switch. And then there's the front gang, which, even though it's basically the same as this, 6 of the positions are tied together and the other 6 are tied together, making it essentially a 2-position switch. You're either in the millivolts ranges or you're in the volts ranges, and that's all it does. Across that switch are the 2 attenuator resistors. There's this big wire wound resistor up here, and then just a small, I don't know what it is, very small, like 1/8 watt resistor down there. That's the one that only sees millivolt voltages across it. And then there's a capacitor across that for frequency compensation, and there's a trim capacitor in parallel with this resistor here also for frequency compensation. This capacitor here is probably going to be the input coupling capacitor, which blocks any DC component of the input signal and allows only the AC component through. This capacitor and this capacitor seem to be orange drop type, which are considered to be extremely stable in terms of their capacitance, and they don't change very much over temperature, although their exact value is not critical in this meter. They should not require replacement due to age, unless there's a reason to doubt their condition. There are a total of 6 ICs in here. These two are actually not regular ICs, they're simply matched transistor arrays. They're the same kind. Each one has 5 NPN transistors that are well matched, and also by being on the same substrate, they're going to have their temperature coefficient affected in the same way by all 5 transistors with any temperature changes on the IC package. There are 2 op amps here, each one in an 8-pin DIP package. And then the other 2 ICs are these very old Fairchild linear adjustable voltage regulators. Kind of an antiquated type, but they work. There's a fair number of transistors on here. Those 2 transistors that are in there, right about in the middle of the screen, they're in little tiny plugs, allowing them to be easily removed if necessary. And I presume that's because, being at the very front end of the meter circuit, they're probably the most susceptible to being zapped by inappropriate connections to high voltage, or voltage surges or spikes, large static discharges, whatever. There is some protection circuitry on this, but it's pretty simple, just simple diode clamps. So I suspect that's why they made those sort of socketed. I see a lot of ceramic capacitors here. These are all just for compensation and stabilization purposes. For example, of the 4 transistors in this package, there's 1, 2, 3, 4 capacitors which go across 2 pins of each transistor, and that's just to compensate for some characteristics of the transistors, and I suspect that these ones here are for the transistors in here, those that need it. Not all the transistors are used in these 2 packages. There's some small electrolytics. Some of these look like they may have been changed. The ones that are blue, those look more modern. These blue ones here are Nichicons, and those are pretty good quality. But there's also some of these pretty old ones. TI brand. These are probably the originals. The blue ones, again, might be replacements. But I'm kind of inclined to just replace them all. They look fairly accessible. Some trim pots, 1, 2, 3, 4, 5, 6. None of them are multi-turn types. And then there's also this potentiometer here. This is the one that's coupled through to the decibel offset knob on the front panel. All these other ones are for calibration. Here's where the rear panel banana plugs are located. Not a whole lot of chassis wiring on this. And the back side of the meter, it's a 200 microamp, 700 volt type. I was incorrect. That one orange drop capacitor on the other side was not the input coupling capacitor. This blue one here is. And I believe that's also a type that's pretty stable and reliable. I should not have to replace that. This one resistor here that's just floating in space is on the negative side of the, or minus side of the meter, and that's actually turning this 200 microamp meter into a voltmeter when you put a resistor in series with it. So it's essentially a voltmeter in this configuration. The two switches here, all they really do is decide whether the signal gets routed through the logarithmic or logarithm converter circuit or not on its way to the meter. And it also, because of the way the circuit works, one of the outputs, the volt one and the decibel one, those two, one of them is inverted from the other. So one of them would give you a minus output while the other one gives you a positive output. And so it's necessary in one of the switch positions, when you're in the dB mode, the switch down here is wired to swap the polarity of the meter when it's connected up to the rest of the circuitry. So that's all that's going on there. You can see right here where the black banana plug is connected straight through without electrical insulation to the chassis, and then a wire that runs up to the printed circuit board. Here's the high voltage shield, and all that does is it covers up the power switch and the neon lamp for the power indicator. Heathkit was starting to be more careful about things like that by the time we got to this point in time, although they didn't in any way cover up the power transformer. Here's the back side of the voltage selection switch, and there's the one and only fuse. I think it's 1/8 of an amp fuse, slow blow. And there's a capacitor which is wired directly across the incoming hot and neutral wires on the power cord. That's not really considered safe anymore. I may be looking into replacing that with one of them that has the safer rating that modern devices are required to have. And all we have otherwise is the back side of the circuit board. The soldering quality isn't great, but it's not terrible either. So I don't think I'm going to go through and resolder everything. But I think I am probably going to disconnect this board. It shouldn't be too hard. There's, you know, a handful of wires that come from the front panel switches, which go up here in a few places. I would have to desolder those, and then these wires that run to the rear panel switches, and I'd have to dismount the front end of the selector switch from the front panel. But I could get this out and then get at all these capacitors in order to change them out. Alright, to give a little more details on the layout of the circuit board, this whole area here from the notch out, the whole area that has the gangs of the range switch on it and the decibel adjustment potentiometer, right up to there, that whole rectangle, that includes the front end attenuator circuit and also the preamplifier. That's the FET and the bipolar transistor down there and some of those other parts. Those are the preamplifier. All these resistors here, that group of 6 of them there, those are the range attenuator. The way it's set up is that there are 6 resistors, but they get used twice. So for example, this resistor might be the top position of the voltage divider, And then depending on whether this switch up here is in the millivolt range or the volt range, then it pre-attenuates, so it can reuse the same resistor ratios here, and therefore you get an effective 12 positions of attenuation out of it. The front end attenuator and preamp is followed by the main amplifier, and that's pretty much this whole section right about here, up to and including these two axial lead capacitors, so an area about like this. That's the main amplifier. Then over here we have the power supply. It goes up a little higher, but it doesn't go up to these potentiometers, so it includes diodes here and these diodes here, and the two linear voltage regulator ICs, these capacitors, the Zener diodes are here. That's what knocks down the plus and minus 20 volts from the regulators down to plus and minus 12 volts. And then we just sort of continue with the signal path, which has been coming like this, and it wraps around everything to the right of these op amps, down kind of over to here, and back down and over. This is the AC to DC converter, otherwise known as the precision rectifier circuit. That converts the AC signal to DC, which is what's needed to drive the meter and the following circuitry. And then what's left is, again, this area, including the two op amps, down to here and over. This is the logarithmic amplifier, or logarithm amplifier. It's what converts the DC signal from the AC to DC converter and converts it into the logarithm that's used to drive the meter when you're in dB mode, and also drive the rear panel output jack that outputs the 3 volt full scale dB output signal. So that's what's on the circuit board. One thing I probably forgot to mention earlier is this strange capacitor here. It's an aluminum electrolytic, but it's got the pinch that usually designates the positive end at both ends. So it's a unpolarized capacitor. This one's actually marked with pluses at both ends, and I think that's all it really is. I think it's really just two regular axial electrolytics with the plus ends facing outwards and the minus ends tied together internally. That's the way you would make it out of discrete components. I think this is really just that same construction inside. If I had to replace this, I would probably just make it out of two regular ones. I've redone the input wiring, positive jack through the coupling capacitor, and then to one of these 2mm banana plugs. This is the plug side, some shrink wrap on it, a new piece of 22 gauge test lead wire from the black or minus input to another 2mm banana plug with shrink tubing around it. This will go to some short pigtails coming off the circuit board, allowing it to be easily disconnected. And I've re-terminated the center tapped secondary of the power transformer to just some Molex plugs I had in my parts bin. Wished I had a 3-pin, but I didn't, so I used two 2-pinners. This one has the outer sides of the winding, and the single one on its polarized point has the center tap. I I've notched out the circuit board. Not strictly necessary. There's an area there with no foils. The original transformer wires are barely long enough to snake around behind the circuit board and then immediately terminate on the component side of the circuit board. And putting these on here, there just isn't enough room so to go that route. Instead, they're going to cut under the circuit board about here, and then there will be enough room on this side to manipulate them and put them on some short pigtails coming off the circuit board over in this corner. Alright, the board has been recapped. There were a few that apparently a previous owner did, and they checked well. So I replaced, this big blue one was there. I replaced these two large black ones, and also this little guy there. The new one's much smaller than the original. There's this one up here, same kind. This big axial one, these two big radials. This little squeaker up here, 5 microfarads. And also these two here, blue ones that are on the outputs of the linear voltage regulator ICs. So I think all the caps on here are up to date now, either by me or by the previous owner. And some of these that I took out, even though the meter was basically functioning, one of them had a ESR of about 8 ohms, which was really high, but it didn't keep it from working. Alright, there are the new plugs on the circuit board for the secondary of the power transformer. They'll connect up with the leads that come under in this notch. And there I've got the 2 input leads for the red jack through the capacitor and the black jack. I have the female 2mm banana sockets on these, shrink tube insulated. Alright, I have one of the prefabricated ribbon cables with connector soldered up to the rear panel jacks. There's only 4 wires, including the one for the ground. And here I have the opposing connector going to the 4 locations on the circuit board. I would have preferred to have slightly longer wires on these, but they didn't come with quite long enough wires. It won't make a difference. This will still plug into the other end with plenty of slack wire. It won't be pulled tight or anything. Alright, I've got another half of a cable connector going to the switches here on the front panel. 2 wires per switch. That's not counting the power switch. A little tricky to get in there with the soldering iron, but after some cussing I managed to get it done. This will have enough wire to go up over the top of the circuit board, just barely. So I need to make sure that the other half of the cable, when it joins up around here, has enough length to reach everywhere on the circuit board. It should, because the top of the circuit board is about here and the wires go almost all the way down to the bottom. So I think it'll work. Might be a little tight, but it should work. And the circuit board comes a little bit shy of the top here, so there should be room to go over the top of the board without getting smashed between that and the cover. The original wires kind of ran in a bunch around this way, and I suppose if it doesn't go over the top, then I can still kind of squeeze them around this way and come in around the front of the circuit board and get to it. So there's some flexibility here. And alright, so I've got that one soldered up now to the circuit board. I've got it so if the wires come over from the other half over the top of the board, it has positionability all around here. If it comes around this way, it can do that. The only thing I can't do is go all the way around here, but this is where the meter is, and that's where the wires would come through, so it definitely has positionability in here. Now, one thing I did deliberately here is I put the male connector for the cable going to the rear jacks, so that's male, and then I use the female one for the one going to the switches. That way I can't accidentally forget which one gets plugged into which. They have the same wire colors. This can only plug into the one from the switches. This can only plug into the one from the rear panel jacks. Alright, there's the circuit board put back into the case. I plugged the banana plugs together, and as expected, there is no place where the shrink wrap insulation is not covering. It butts up very nicely. My only concern is that this component is now, this capacitor is now unsupported really, except by one lead, but it's a lightweight component. The leads are very thick. It's only a short distance. I'm not worried about it. I don't think it'll ever break off, even if this is bounced around a lot, which it's not gonna be. The ribbon cable from the switches goes around behind the meter very nicely, close to the way it used to, and comes around this side and connects up pretty as you please. This one down here is connecting up just like it should. The transformer secondary wires go through that notch I made, and those are plugged up very nicely. So that completes the work that I'd planned by way of fixing this up and making it as right as possible. All the electrolytic capacitors are replaced except for the one, that blue one right in the middle of the picture. That's bipolar or unpolarized, and it tested good. It's hard to find. It's an important component value for the way the circuit works. I could not find any unpolarized caps of that value. I could have made one out of a couple of electrolytics, but even then I wouldn't have got the exact value. That's probably a part that Heathkit had made special. They did that a lot. So it's testing okay, and I'm just going to leave it in there. It's the only electrolytic that's still in here. I decided not to change this capacitor with a safety cap. In my collection, this is probably never going to get powered up again except for occasional demonstrations. The case wasn't very dirty. I did take the knobs off. You have to take them off to get the switch out so that you can remove the board. I did clean up dust off the push button switches and around on the knobs. I took the knurled ends off the banana binding posts, soaked and cleaned them with a toothbrush, got the dust off. So the case itself is clean. There was no need to go over it with alcohol or anything. I just realized that the model number label is missing. This line had them as a long skinny label that would go in that recessed area on that extrusion there. I've had that happen once before, and so I did like I did then. I just made up a new one on laser printable plastic with permanent adhesive on the back, and I'll stick that on there. And there we go. Alright, I just finished going through the calibration procedure. Some of that involves hooking up to various transistors with combinations of the input shorted or not, and another jumper between 2 points on the circuit board, and monitoring with a DC voltmeter and dialing in most of the pots, and then connecting up a signal generator of known frequency and amplitude, and dialing in trim capacitor over here, this one down here, and a couple more of the trim pots to get specific readings on here. And I found that it really didn't need any calibration. Everything was pretty much dialed in, so the previous owner had it about where it needed to be. Let's take a look at the Heathkit manual. Start out with the warranty, a list of Heathkit phone numbers, a photo of the meter itself. The manual is copyrighted in 1976, so this is, if there's more than one version, this is probably the first one. Table of contents, parts list, this is referring to parts identification diagrams that are in the separate illustration booklet, not in the manual proper. Then step-by-step assembly instructions, talking about basic tools that are needed for assembly, soldering information, and then launch right in to circuit board assembly. Combining that with further instructions on soldering. Just keep working away across the board, putting on resistors mostly, and then building up the taller devices. The IC sockets are put in, and then capacitors and transistors and trim pots. And then putting on the range switch. Some of these components have resistors put directly across capacitors. Chassis assembly. Mounting the switches, fuse holders, LED lens, power light lens, banana jacks, power transformer metal bracket, power cord strain relief, high voltage shield, mounting the circuit board assembly into the chassis, and soldering up the couple of components that are just run between chassis items and items on the circuit board. Putting on the knob. Calibration initial tests. There are separate instructions for calibration if you don't have any other equipment. There is a method for using just resources built into this meter, and then there's calibration using external test equipment in the form of another voltmeter, high impedance voltmeter, and a signal generator. Final assembly of the chassis, putting the handle on. Operation. Applications in case of difficulty. specifications, circuit description, and Heathkit kind of ran the gamut in the quality of their circuit descriptions. Some of them, they obviously had a very thoughtful and thorough author, and there's other ones where the person is just a bad writer or was just impatient to get it over with and thought, oh, they'll never read this anyway, I don't have to put any work into it. This particular manual circuit description is pretty poor. It obsesses over some trivia and then completely leaves things out, doesn't describe them at all. And the most complicated circuit in this is the log converter. It's about 1 page of description. It needs more, and at least 2/3 of what's here is just explaining a feedback path issue, which is a nice curiosity, but they could have spent more effort describing how it really works instead of just covering that one little part of it. There's a little bit of power supply description on the next page. Semiconductor identification charts. And then parts request forms and customer service information. Here's the illustration booklet. Has a number of pictorials. The circuit board X-ray view. Here's the parts identification diagram. Chassis assembly, wiring of the front panel push buttons, wiring of rear panel jacks and AC power related components. Some assembly details for the front of the chassis. Connection of the switches and the meter and the rear panel jacks. Description of the front and rear panel controls, jacks, and other items. And while this looks like a wiring diagram at first glance, it's really a diagram just showing the adjustments that have to be touched during the calibration, just highlighting them. And then one more pictorial. Seems to be about the high voltage areas. And also points out where the mechanical zero adjust for the meter movement is located. And then there's the big fold-out schematic diagram. It's not a terrible schematic diagram. I've already found some errors in it. It seemed like at least a couple of the trim pots I looked at on here are depicted incorrectly in relation to how their wiper is connected to one end or the other of the pot and their rotational direction. I think there were a couple other things I noticed already. I can't recall what they were at the moment. That were mistakes. But basically an okay schematic. I did redraw it as part of my circuit study, and when I get into the description of the circuit theory, I will be using my sketches rather than this. It's just easier to see what's going on. Alright, a little bit of a demo. I've got it in volts mode and the 300 millivolt range. That would be 300 millivolts full scale, which means it should be around here on the scale. And I just need to make sure I'm putting in a appropriate signal. I've got a sine wave dialed up, 1 kilohertz, and I'm going to put in the amplitude of 300 Yeah, 300 millivolts RMS. And it's right on the money. It's sitting right there on the 3. If I change the amplitude to 200 millivolts, it goes right there. 100 millivolts, it's right there. So it's good on the 3 scales. The only other difference between the 3 scale and the 1 scale, or the 300 millivolt and the 1 volt, any of the other scales starting with 3 or the ones starting with a 1, are different only in the sense of the attenuation resistors, and they have nothing to do with calibration. So if I get reasonable readings on both of those, then there's nothing more I can do. So I'll go up to the 1 volt scale now, and I'm going to put in 1 volt, amplitude 1 volt, RMS. So it's a 1, it's going to go on the 10 scale, and it's right on the money. I put in 900 millivolts RMS, and on the 10 scale it's sitting right about at 9. 8, 7, 6, 5, 3, 2, have to take into account the parallax, 2, and 100 millivolts. And basically down to 0. So this is showing very accurate. Now let's go back to an amplitude of 1 volt RMS, right up to the top, and actually I'm going to change it to 500 millivolts. So 500 millivolts RMS, right in the middle of the scale, and I'm going to go up to the frequency and change it to 500 kilohertz. 500 kilohertz, and it moved a little bit, but not much. So it's pretty well frequency compensated. I put in 1 megahertz, which is the top rated frequency for this, and it's still sitting really close to the 500 millivolt, so it's doing a good job there. Alright, I've got it set to 100 volt full scale. I've got it connected up to my Variac, and also simultaneously to my digital voltmeter. It's reading a fraction of a volt, and it would be here too if I was on a lower scale. There's a little bit of voltage there, even when the Variac is dialed all the way down, so it's essentially 0. Actually, that was floating. I didn't have it really connected to the Variac. That's probably why it was picking up some voltage just from the air. This should be somewhere in the ballpark of 50 volts. And it's reading 51.7 up there. So let me dial that in to essentially 50 volts. And it's really close. It's just a hair on the low side of 50. So let's take her up to okay, that's 100 volts on the other meter, and it's sitting right at the full scale here for a 100 volt scale. So again, pretty darn accurate, as good as one could hope for on an analog meter. I have run through the dB circuit in the calibration procedure, so I know that works, but rather than get into logarithms here, I'm just going to leave the demonstration at this point. The only difference between the two is that the signal runs through the extra dB conversion or logarithmic conversion circuit on the way to the meter movement. And I already know that works, but trying to show you a number without explaining the math. It's not worth the bother. I just know that it works from the calibration procedure. Alright, here's the beauty shot. Alright, I'm going to go over the circuit theory using my redrawn sketches. Well, they're redrawn and they're sketches. They're not redrawn sketches. I have it on 3 sheets. The first sheet includes the front end attenuator, the preamp, the second stage attenuator, and the main gain amplifier and buffer. The second sheet includes the precision rectifier and its buffer, the meter circuit itself, the actual meter movement, the logarithm converter, which is required to derive the decibels from the voltage, and the associated buffer, and the regulated power supply. I'm actually going to start this explanation with the power supply since it's the simplest. We have the AC line cord. There's the capacitor across it to reject voltage spikes. On modern equipment, this is a safety capacitor. On here, it's just a regular high voltage ceramic disc capacitor. Then you have your fuse, you have your power switch, which is a push button on the front panel. And then it's a typical dual primary winding power transformer. 2 identical windings, and they can be wired in series or in parallel depending on whether the line voltage is 120 volts or 240 volts. It's shown in the 120 volt configuration. So the hot comes in here and it goes to the top of this coil. It also goes through this switch and to the top of this coil. The neutral comes to the bottom of this coil and through the switch to the bottom of this coil, so they're wired in parallel. Even if you had this connected up to 240 volts and put the switch in 240 volts, then you'd have the hot up here, the neutral down here, and these 2 points connected together through the switch. Thereby it would be splitting the 240 volts into 2 halves, one for each winding, and that's why the power on neon lamp and its current limiting resistor are shown connected across only one of the windings. The secondary is a standard center tap secondary. The secondary winding is 46 volts center tap approximately, so it's 23 volts from the center tap to here, 23 volts from the center tap to here, or about 46 volts from here to here. The center tap is grounded. You have a full wave bridge rectifier, so that gives you, with the filtering of these 2 capacitors, approximately 29 volts here and approximately minus 29 volts here. We have these 2 linear voltage regulators, this old-fashioned 4-pin type by Fairchild, the MU-A78MGC or MU-78MGT2C. It has an input and an output and a common pin, just like a 3-terminal linear regulator would have. Same thing here. It also has a control pin, just like the adjustable 3-terminal regulators use instead of a common pin. This one has both. So these are both connected to circuit ground. And then in order to produce the desired output voltage, you have a voltage divider. If you didn't have 2 of them in a tracking configuration like this, where they have the same voltage but opposite polarities, you would only have 2 resistors in the voltage divider. This one and this one going to ground, or this one and this one going to ground. But in this case, since they're tracking, you use 3 resistors connected between the positive output and the negative output. And you set it up so you have ideally 1 milliamp flowing through there. And then you set up the resistor divider such that you end up with plus 5 volts here when this is correct, and minus 2.2 volts here when this is correct, because these regulators will adjust the output voltage until this one gets plus 5 volts and this one gets minus 2.2 volts. And with these resistor values, that's what it produces. So you've got plus 20 volts and minus 20 volts regulated. Stabilizing capacitors going to ground. There are jumpers on the circuit board. It's not clear why. I think it's just because it's a single-sided circuit board, and there's a number of other jumpers on the board too, just to get the foils to go places that there's other foils in the way. So I don't think it's for maintenance. It's just a construction convenience or board layout convenience. So you still have plus 20 volts here and minus 20 volts here, and those are used by various points in the circuit. We also need plus and minus 12 volts. So there's a 12 volt Zener, another 12 volt Zener, both referenced to ground. Each one has a current limiting voltage dropping resistor on each end. So you end up with plus 12 volts here and minus 12 volts here. Alright, here's the second page of the schematic. I'm going to zoom into the first circuit of interest, and this is the primary attenuator. You have your input jacks here, one marked red, one marked black. It's for AC, so it wouldn't matter much, except it's useful to know which one is tied to earth ground. So I think that's why they use the color coding, so you wouldn't try connecting AC hot to here. The highest full-scale range on the meter is 300 volts, but the circuit is designed to withstand up to 600 volts without damage. So it's 600 volts max, 300 volts useful. This terminal is connected, besides to chassis ground, also to circuit ground. And this terminal goes through a capacitor. This blocks any DC component of the signal being measured, so only AC gets through, and since it's an AC meter, all we want to look at is the AC portion. And then really all there is to it is 2 resistors, a voltage divider and a selector switch. The ratio is 10 megohms over 10 k ohms, a 1000 ratio. So this produces a 1000 to 1 voltage divider. Whatever is here, there's 1,000th of it here. For any voltages less than 1 volt, this switch is in this position. For any voltage 1 volt and higher, the switch is in this position, so you knock the incoming signal down to 1,000th of that value. This isn't really a 2-position switch. It's actually a 12-position range switch with 12, like I said, 12 positions. But for the sake of simplification, I use this terminal to represent 6 positions all tied together, and this terminal to represent the other 6 positions all tied together. So it functions as a 2-position switch. 1 millivolt through 300 millivolts, 1 volt through 300 volts selected there. So that's the primary attenuator. I left it off of this sketch, but these 2 resistors have parallel capacitor. There's actually a trim capacitor across this resistor and a fixed capacitor across this one. And those provide frequency compensation. This circuit can work over a range of something like 10 hertz up to close to 1 megahertz. And you need to make small tweaks to the voltage response of the circuits when you get into wide voltage ranges like that. It's conventional to put some compensating capacitors across attenuators. I won't go into it further than that, but just picture a variable capacitor here and a fixed capacitor here. This circuit here is a preamplifier. It's also an impedance converter. So we can use fairly high resistance values here and not have a problem with that because the impedance here is so high. And to get that high impedance, we have an FET front end. To protect the FET, we have two diodes and a resistor. This diode is going to an approximately plus 12 volt power rail, and this one's going to the minus 12 volt power rail. This isn't actually going to the plus 12 volt power rail. It's actually going through this resistor to the plus 20 volt rail, and all these resistances here along with this form a voltage divider that leaves us with approximately plus 12 volts here. Not really sure why they did it that way instead of just using the 12 volt rail, but it may have something to do with the clamping function here. Beats me. Anyway, these diodes limit the signal to no more than plus 12 volts or no more than minus 12 volts approximately. And any difference in voltage is dropped across this. Ordinarily, you shouldn't be anywhere near plus 12 volts or minus 12 volts if the range switch is selected properly for the input voltage. But if you have a careless user, or if there are voltage spikes on the input, this should take care of it. Now this circuit here with the FET followed by the PNP BJT transistor, I'm going to go and digress slightly to show a simplified version of this. I made this little sketch on sheet 3. This shows a little circuit called the Sickly pair or Sickly pair. It's spelled S-Z-I-K-L-A-I. It's named after somebody of that name who invented this circuit. It's sort of a variation on the Darlington pair, which is a classic arrangement where two BJTs are connected together in a similar arrangement in order to get more gain than either one of the transistors has by itself. And you can also look at it as if you have a power transistor, you'd use the other transistor as a driver for the power transistor. That's the way Darlingtons are usually used, one of those two ways. But Darlingtons have a problem in that the two base to emitter junctions, which are typically 0.6 volts, add up. So you have a pretty high base to emitter voltage on a Darlington of 1.2 volts, and that can be a problem in some circuits. So one of the things Sickly came up with was to use the NPN and then follow it with a PNP connected in this fashion. And the way these two work together, it acts like one big transistor, with this being the base, this being the emitter, and this being the collector. So these definitions here follow the NPN, and the PNP is being used in a somewhat unusual way, but it has the result of having more gain while still behaving like a single transistor and having only the 0.6 volt base to emitter voltage. The Sickly pair is also called a complementary pair, and also sometimes called a complementary Darlington. Complementary because the two transistors have to be the opposite types. You can have an NPN followed by a PNP, or a PNP followed by an NPN. There's also a circuit called the hybrid Sickly pair, and you replace the first BJT with an FET, but otherwise the configuration is similar. If you connect up an FET like this, it's called a source follower. You put in your input signal, you have the high impedance here that the FET gives you, much higher impedance than the BJT would here, and then the voltage at the source follows the voltage at the input. But it doesn't have much drive capability. Its output impedance is low, but it's not as low as you'd probably like in many circuits. So it's very conventional, and pretty much all the Heathkits I've done videos on have this configuration unless the signal goes straight into an IC. Almost all the other ones use some variation on this circuit. So you have a resistor on both the source and the drain of the FET, the output's taken off the source, and then you have a PNP connected up, sort of piggybacking on the FET, and it does a similar thing to what the second transistor did in the normal Cycli pair. So, hybrid Cycli pair with a higher input impedance and the low output impedance of the normal version. So going back to the actual circuit here, you'll see that we have resistance from the drain to the positive power rail and resistance from the source to the negative power rail. There is a capacitor across this resistor for stability, and I think it also has some effect on the frequency response of this circuit. This resistor is split into two so that we can make one of them adjustable, and by doing that it changes where in the overall voltage span this can deal with. It changes it so that this one is operating in its optimal range of voltages. So it's basically changing the bias on this. Heathkit says it's the way that you can adjust the collector of this one to be in its happy place. That's one way of looking at it. This is almost like some feedback here. It's certainly a variation on the classic hybrid Cycli pair arrangement, but instead of just connecting this to this, we have this extra resistor in here. The output is still taken from the collector of the BJT. Alright, we have a 12 position range switch, but this front end primary attenuator only has two ranges. It has the one for the millivolts and it has the one for the volts. So we have to split both of these up 6 ways in order to get the total 12 ranges that the meter actually has. So that's done by the secondary attenuator. So it's just another gang on the same switch as this one, but here I've depicted it as an actual selector switch. 1 millivolt, 3 millivolts, 10 millivolts, 30 millivolts, 100 millivolts, 300 millivolts, then into the voltage range is 1, 3, 10, 30, 100, and 300. You'll see that the 1 up here is connected to the 1 here, the 3 to the 3, and all the way up the 300 to the 300. So when you move this switch from here to here, for example, it makes no electrical difference here, but the corresponding switch here has shifted gears from this position to this position. And that's how we keep it in the millivolt ranges here and the volt ranges down here. All these resistors add up accordingly to get the proper ratios, and if everything's working properly, and assuming you don't exceed 600 volts out here on the input, you'd have a maximum of 0.6 volts here. Normally it'd be a maximum of 0.3 volts, or depending on the range, it's always going to be 0.3 volts maximum, but because the circuit allows 600 volts, it would be 0.6 volts here. So we have another protection here. Instead of diodes clamping like this, we just have a pair of inverse parallel connected diodes to ground. So if this point gets to be more than 0.6 volts, it forward biases this diode and connects it to ground, shorting the input out. If the voltage here gets to be less than minus 0.6 volts, then this diode becomes forward biased, and again it shorts this point to ground through this diode. There's also a resistor here to make sure we have a ground reference on this signal. It is capacitively coupled back here, I didn't mention that. It is normal practice in any AC amplifiers to put coupling capacitors between each stage so you don't accumulate DC offset just due to small DC errors creeping into each stage. And once you do that, you need to re-zero it, or if not zero it, at least referencing it to whatever voltage you're calling the common at that point. In this case it's ground, so resistor to ground. Alright, here's the main amplifier, as Heathkit calls it. It's a fairly simple circuit in principle. It's gonna act like a simple op-amp circuit. And we start out with a differential input stage, a differential amplifier. It's a classic configuration where you've got a couple of NPNs here of similar, well, it should be as nearly identical as possible, characteristics between them. Their emitters are tied together and then through a resistor to a negative potential, in this case minus 20 volts. Some more advanced circuits that do this replace this with a constant current sink to a lower potential. It works either way. This is less stable, less precise, but good enough for the specifications of this meter. You have resistances going up to a positive voltage potential. In this case, I didn't show it in there. I'm going to have to fix that. In the words of Big Clive, one moment please. So there's the plus 20 volt power rail serving this whole amplifier. So the way these work is that if you had both of these just tied to ground or to the same voltage, you'd have the same current flowing in this path, same current flowing in this path, and if you're measuring across the resistances here, you'd get the same voltage, you know, for example from here or here to ground. This is a little fancier because it has a tap between these two resistors, but we don't care about that for the purposes of this explanation. If the voltage here goes higher, then this side conducts more, and because these are balanced, you tend to get less current in this side. If this input here goes to a lower voltage, then this side conducts less, and this side will conduct more. When you conduct more or less through this transistor, the voltage drops on these resistors change, and that's where the output of the circuit is taken from, or at least from the differential amplifier. This is being used in a feedback capacity. If you're looking at this as an op-amp, this would be your positive input, and this would be your minus input, or inverting input. The voltage across this resistor is brought over to this BJT, which is conditioned with a diode here. All I can see that does is provides a bit of a voltage drop. It could be there for some protection capacity that I'm not thinking of. And its resistor to minus 20 volts is clamped with this diode to ground, so if this point goes lower than minus 0.6 volts, then this diode will become forward biased and clamp this to minus 0.6 volts. I'm not sure why that's necessary here, but that's what's being done. So apparently, the way with the 0.6 volts here and any gain that might be here, and there's probably not very much, you're not really expecting this point to go lower than 0.6 volts anyway. We haven't really had a voltage gain in this, not at least up to this point. Anyway, this then comes over into this, which is a amplifier. It's a voltage amplifier, and that boosts the output, and then that goes into a final stage, which I believe this is only a current gain, not a voltage gain here. And this is the actual output of the main amplifier, this whole thing, This is the output. And it's used out here in a couple ways, but we also have to have feedback. There's a lot of stages that either have voltage or current gain here. And to make this precise, it needs to be precise since it's a piece of test equipment. None of these are completely linear, so you have to have some form of feedback. There's actually two feedback paths on this. There's an AC feedback path and a DC one. For DC, we come through this resistor. There's a capacitor filter through a very low resistance to ground. This might actually just be here because it was inconvenient to get this capacitor to ground on the circuit board, and that's a trick that's often used. Just put a low value resistor in and treat it like a jumper. But it may have some influence there. Anyway, it's essentially a pi filter, two resistors with a capacitor to ground. And then it comes over here and it produces a voltage drop across these resistors, and that voltage is fed back into the negative input of the differential amplifier. So if this whole thing were an op amp, you'd take the output, feed it through some resistors, and take it back to the minus input, and you'd have an inverting amplifier. And you'd have negative feedback because the input's being brought to the positive input or the non-inverting input, and because of the inversions of these stages, you end up with a positive voltage out here. With the gain afforded here in voltage, it's about 3.5 volts when the meter's at full scale. There's also AC gain. So we come out of the output, we have again this resistor, which is really just the resistor from this point to ground. It's just shown way down here. We go through a capacitor, so we're not dealing with any DC component in this feedback path. We have a resistor. It's adjustable because one of the two resistors is a trim pot. This is our gain adjust. It's AC gain. It drops its output voltage across this, or you could look at it as this whole thing's just a voltage divider, and we're coming off of this point, going through this resistor, and back to the inverting input of the differential amplifier. So we have some DC gain, and then on top of that we have AC feedback. And we can adjust this. This is the main calibration point for the whole meter. And then that output goes off to the next stage in the circuit, the precision rectifier, also known as the AC-DC converter. We also go through a voltage divider that's 1500 ohms over 426. It's roughly a 3-to-1, so it takes a third of this voltage, a little bit less than a third. Again, this is expected to go to 3.5 volts full scale. And with these resistor ratios here, you end up with 1 volt when the meter's at full scale. Now, this is an AC signal, and it's 1 volt peak when the meter's at full scale. And it's capacitively coupled to make sure we don't have any DC component that could get out and skew this. And as is the case elsewhere in my sketches, I leave off some various compensation capacitors. There's about 3 of them in this circuit that I'm not showing. I think there's probably one from here to here, and there might be some around these. I'd have to go back to the main schematic to see, but they're not necessary for basic understanding of the circuit. That's why I left them off. Here we're moving up to sheet 2 of the sketch. I'm going to zoom in here to a pair of subcircuits, the precision rectifier and the buffer amplifier. So we can treat this as one circuit and this as one. In many of my other Heathkit videos or just other test equipment videos, there's often the need for a precision rectifier circuit to convert AC to DC for display by either a physical meter movement or by a digital meter circuit that responds only to DC inputs. You want to convert the AC to the DC in such a way that it remains proportional in voltage. In most modern circuits, this is done with an op-amp that has the input fed into the plus input. The minus input is fed back with a resistor to the minus input. That gives you a constant feedback path if there's no other path at the moment, so the op-amp doesn't go off into the wilderness at various points. And then there's also an AC feedback path, which is through one or two diodes facing in opposite directions, and that's the primary AC path for feedback. But sometimes those diodes aren't conducting, and then those feedback paths are open, and you still need that DC feedback path to keep the amplifier in check. The way the precision rectifier works and why it's called precision is you could just use a diode rectifier or a diode bridge to convert the AC to the DC, but at lower voltages, when the voltage is below the forward bias of the diode or diodes, then they don't conduct at all, and it's like an open circuit. And then if you do get them to conduct, there's a 0.6 volt approximately voltage drop across them, so you've already lost some accuracy. And that would traditionally be taken care of on old passive multimeters and VTVMs and things like that, by simply making the meter face have scales separately for AC and DC, and having them scaled to compensate for that voltage drop in the diodes. The precision rectifier puts the diodes in the feedback path in such a way that the op-amp's natural tendency to adjust its output until the feedback is equal to the input. If the diodes are in the feedback path, then the op-amp automatically increases its output by about 0.6 volts to compensate for the 0.6 volt drop in the diodes in the feedback path, and therefore it's correct. What we don't have is an op-amp here. It's done with discrete transistors, but as was the case with the main amplifier I talked about just a few minutes ago, we have a very similar circuit up front. It approximates the front end of the op-amp. So if we're calling this the negative or inverting input of the equivalent op-amp, then this would be the positive input, and it's essentially tied to ground through a 100 ohm resistor. So you could think of this as being the plus input of the op-amp just tied to ground, which is the way it usually is on an op-amp based precision rectifier. So far it's very similar. We have the normal resistor from the positive supply rail going to the collector of each of these two. They share the common emitter, which goes through the resistor to a negative potential, in this case minus 12 volts. So yeah, it's again a differential amplifier, and it has a current boosting transistor stage on the output, so that we have the ability to drive some other circuitry from this. Now, in addition to, oh, and by the way, and this is where the feedback through the diodes goes. On the positive half cycle of the AC, this diode is forward biased, and this is the feedback path back to the inverting input. If we're on the negative half of the AC wave, then this is the diode that's conducting, and this is the one that's in the path. But as I said before, there are times when the signal is so low that neither of these diodes are conducting. It's below their minimum turn-on threshold, and therefore both of these paths are open. So that's why we need a DC feedback path or some way to deliver equivalent current, so this amplifier doesn't just try to drive towards the maximum output plus or minus to try to keep it stable without jumping all over the place when we don't have either of these feedback paths. And as I said before, usually that would be accomplished with just a simple resistor from the output of the op-amp back to the inverting input or minus input, but that isn't exactly being done here. What we have instead is we have this resistor pair coming off the positive supply rail. It's adjustable, and it comes back through this resistor and ultimately back to the input of the whole amplifier. So this is a way to get some sort of feedback when nothing else is there. There's also a bias here for this first transistor. We have a resistor from the positive supply rail and one going to the minus supply rail. And this is adjustable in 2 stages. So there's kind of like a coarse and a fine. This one's 100K and this one's 5 mega ohms. So you would adjust one and then fine tune with the other. And the fact that they used 2 trim pots like this suggests that it would be a touchy adjustment to make if you didn't have it set up the way it is here. So we've got all that. It's so far, again, very similar to a traditional op-amp based precision rectifier. The output is taken off of one or the other of the feedback paths. It doesn't really matter which one. In this case, it's taken off the negative feedback path. So when we're in the negative half of the wave, and this guy is the one that's conducting here, so the feedback path has current going around this way, then the voltage can be tapped off of here. It's after the diode, but that doesn't matter because the equivalent op-amp functionality of this is boosting the output already to compensate for that diode being there. So the output is taken right here. This is also the junction between the output of this stage and the input of the next stage, and it's also part of the feedback path. This voltage will always be negative because of being in this branch of the feedback path with the diode pointing that way. So no matter what happens, this is going to be some negative voltage. Let's say it's minus 1 volt. Of course, it'll be moving up and down depending on what the signal being measured is. And there's also feedback from this stage coming back around into here, and there's current going out this way, and the Heathkit manual is at great pains. It takes about half a page to say it, that it'll be a little confusing if you're probing around in here with a scope or a meter trying to troubleshoot it, and you get to this junction and it'll always be 0 volts. Well, this is an amplifier with a gain of 1, and if you have negative 1 volt here, by the time it goes through here it'll be inverted to positive 1 volt, and positive 1 volt there feeding back into here, negative 1 volt. It kind of cancels out to 0 volts here, but 0 volts, especially in a bipolar circuit like this, isn't no volts. It's just 0 volts if you're measuring it from ground. But the lowest potential in here is minus 20 volts. The highest potential is positive 20 volts. The voltages can be anywhere in there. So if this is just reading 0 volts, that's only because the thing you're measuring the voltage with has its other probe connected to ground, which is 0 volts. So it reads nothing. But there's still signals going through here. It's just, you know, it's halfway between the positive and minus rail, and it sort of stabilizes at that point. Meanwhile, currents are flowing every which way around here. The signal ultimately gets through. You just can't tell it if you see a 0 volt indication, and it's confusing. That's probably why the Heathkit manual took so much pains to describe it. With a lot of these circuits, it's important to have the circuit track with itself pretty tightly. So instead of using all discrete transistors in here, Heathkit used a special part. It looks like an IC. It's the part number CA3046, and that's a monolithic package which contains only 5 transistors, nowhere near as much as a regular IC would have, but technically it is sort of an IC. 3 of the transistors are individual, and the other 2 are connected together kind of in this configuration right here, which is why it's used here. This is from IC 101 Part A, IC 101 Part B. These are the 2 ones that are joined internally inside the IC package. This is actually a discrete transistor here, but 2 more transistors in this package are used over in the next stage, IC 101C and D. The E part is not used. So we've got the signal here. It's been rectified through the precision rectifier. There is no corruption due to the diode voltage drops. And now we get into this stage, which is really just a buffer. It has another differential amplifier in the front, just like the previous stage and just like the main amplifier that was talked about a few minutes ago. And once again, this input, that would be the equivalent of the non-inverting or plus input, is essentially tied to ground. The output is current amplified through the transistor just like the other 2 places, and we take the signal from the same place. Again, so that the circuit tracks accurately, we have feedback, and it goes into the negative input, but it's mixed with the signal coming from here, and also mixed with whatever voltage or current is the result of this. But again, it's going to be 0 volts, but the currents are still flowing and representing the signal. This particular feedback resistor is compensated with a capacitor across it. And if you think about this as being a simple op-amp and this being negative feedback, when you put a capacitor across a negative feedback resistor, or a resistor in a negative feedback path, it makes it act like an integrator. So it helps it reject spurious signals and be more stable. So we take the output here, and this is roughly a 0 to 3 volt DC signal, whereas the signal coming in was about 3.5 volts AC full scale. Over here it's coming out approximately 3 volts DC maximum, 3 volts representing full scale on the meter. And this goes 3 places, which is one reason why I needed this buffering here. The first place it goes is a pair of output jacks on the rear panel, the DC volt output. One of the jacks is tied to ground, the other one is tied to this 0 to 3 volt DC signal by way of this 2 to 1 voltage divider. Well, it's actually 2 over 1, so it's 2 parts are going to be dropped here and 1 part's going to be dropped here. So you have 3 volts up here, there's going to be 2 volts dropped here and 1 volt dropped here. So we've turned a 0 to 3 volt signal into a 0 to 1 volt signal. The 1 volt corresponds to meter full scale. So this is what you can connect up to an external meter or chart recorder or something else that might need to monitor the signal that's coming into the meter. We also have to drive the physical meter movement on the front panel. This is the dB push button on the front. This is the volt push button on the front. The switch is shown in the dB position with these 2 pins shorted out and these pins on the right shorted out. If you push the volt button, then these would shift over to here and here, and this one would shift over to here. But let's just say we're in the volt mode at the moment, so we have to visualize this slider being from here to here. That 0 to 3 volt signal is going to come through here, go around here, and because we have to be in the volt mode in order to read voltage on the meter, you have to visualize these two sliders as being here and here. So we come around here, we go through here, we come into the plus side of the meter, which is a 200 microamp meter movement. So 200 microamps going through it results in the meter reading a full scale deflection. It has an internal 700 ohm resistance, and if you add that up to the 14.3K here, you add 700 ohms to that, it's 15K. So if you do the math, with a 3 volt signal going through 15K, you get 200 microamps. So it all adds up with Ohm's law. And then it comes out of the meter through that resistor, goes through the slider, which would be in this position, and returns to ground. So essentially what we have is just this meter and this resistor connected from this point to ground. That would be it if we're in volts mode on this meter. But what if we're in decibel mode? Well, the decibel system is just a logarithmic way of representing either simple signals or the ratio between two signals according to a logarithmic curve. That can be useful for certain things, especially for measuring ratios. But this meter has it, so we have to talk about it. That's a large part of the circuitry. So if we're in dB mode, now the switch is in the position shown here, and that 0 to 3 volt signal comes here and it goes through this way, it can no longer go to the meter movement. The meter movement has been disconnected from this direct 0 to 3 volt signal. So the signal comes through here, and it comes around here, and it goes into the logarithmic converter. So I go back to my little sketch on sheet 3, and I showed what's called a transdiode logarithm amplifier. A very conventional way of converting a linear signal, voltage or current, to a logarithm is to, or to the logarithmic equivalent of that input signal, is to run it through an amplifier which has a diode in the feedback path. That, if you set it up correctly, then there's a part of the diode's response which is logarithmic, and you can take advantage of that with it in the feedback path so that you can use it to convert a linear signal into a logarithmic signal. But there's some problems with that. It isn't the greatest. It has performance issues. So they found out that if you use one of the internal diodes inside a BJT type transistor, then that diode functionality in here is actually superior to just a discrete diode. And by using a transistor as a diode, it's a transdiode. What you have here is an op-amp with negative feedback, so the output's going around to the minus input or inverting input. The signal's going into that same input, and the plus input or non-inverting input is grounded. The op-amp is trying to do whatever it can to result in the same voltage here as there is here, namely 0 volts. So an op-amp with negative feedback like this has what's called a virtual ground at its negative input. So it's going to read 0 volts even though current is flowing, and current doesn't flow in or out of the input of an op-amp. So if there's current going in here, it must be going this way, and if there's current going this way, it must be leaving this way. With this transistor's base tied to ground and its collector tied to something which has the same voltage as ground, even though it's not actually ground, it's like shorting out the base to the collector. So the diode that's inside the transistor from base to collector is shorted out in this configuration. But what you have is the diode from the base to the emitter is in the circuit, and its response is logarithmic. So when you use this transdiode amplifier configuration, you put in your linear signal here and you get a logarithmic signal here. So far so good. However, we're not just interested in turning the voltage output of the meter into a logarithm. We're trying to have a proper dB reading or decibel reading that reflects the ratio of the signal we're measuring to a reference signal. And that requires the reference signal to be turned into a logarithm or a logarithmic signal, as well as the signal being measured or the input being measured being turned into a logarithm. So we need two of those transdiode circuits, each with its own op amp. So there are two op amps here, and there are two transistors. And just like with the precision rectifier and its buffer, we're using some NPN transistors that are part of a monolithic transistor package. It's not the same one that was used up here, it's a different one of the same type. In this case we're using IC104 part D and part C. And they're connected together in what looks superficially like a differential amplifier, but that's just because the emitters are tied together. It's not configured that way otherwise. We have the two op amps, and this is the one that's for the reference, and this is the one that's for the signal being measured. Going back to this simpler version, if you have a voltage here and you have this resistor here, the voltage applied across the resistor, and remember this is a virtual ground, so it looks like 0 volts. You have a voltage V in and 0 volts on the other side. There's going to be current flowing through this, and the current is proportional to the voltage difference, but the current can't go into the op amp, so it must go that way. The same thing is happening in this actual circuit. We have this 0 to 3 volt signal coming around here, and we go through this little resistor network. This is the one that's adjusting the decibel offset. This is a front panel control. It's the concentric knob in the middle of the range switch knob, and it has a resistor in series with it, and then that is got a resistor in series with it. This is effectively changing the way the knob works. I suspect that this is a linear pot. I didn't actually scope it out, but by putting this resistor in parallel with another resistor, it changes the response. So when you're turning the knob to its midpoint, you're not giving it half the resistance. You can do the math and see how that works out, but this is a way of turning the curve, if you will, of the resistor change into a different one. But all together this acts like that input resistor in the simpler circuit. So we're converting the 0 to 3 volt signal into a current, and that is going into the minus input of an op amp. The plus input is grounded, and we don't immediately seem to have the transdiode here. All we have is a capacitor. We know that putting the capacitor across the negative feedback path of an op amp acts as an integrator, and just like with the other circuit we looked at earlier, this has the effect of dampening out spikes. It helps with it helps reject transients. Well, we come out of this op amp and we go through this voltage divider to ground, and then we go into the base of a transistor. But in the classic configuration, the output of the op amp does not go to the base, it goes to the emitter. And the other side of the transistor goes to the minus input of the op amp. So what we're really looking for here is which transistor is connected to the minus input of this op amp, and it's this one. So this transistor is the one that goes with this to make the transdiode amplifier. And indeed, its base is tied to ground. And then we have this op amp, also with an integrating capacitor on it, and it drives the emitter of both transistors, not just its own, which would be this one. And indeed, the base of this one is not tied to ground exactly, but it is tied to the minus input of its associated op amp. That point is not at ground, instead it's at something fairly close to ground. Coming from here, there's this 32K resistor and only 1,000 ohms here. So looking at this as a voltage divider, this point is very nearly at ground by a couple orders of magnitude, but it's not exactly at ground. So you can kind of see that, yes, this op amp goes with this guy and this op amp goes with this guy, and they're connected together in a funny way. This transistor's base is really at ground. This one is almost at ground. What does that all mean? Well, the subtlety is that each one of these is doing a signal conversion to a logarithm, and the way these transistors are connected together makes them subtract one logarithm from the other. Remember, we're trying to do a proper decibel measurement, and a proper decibel is based on a ratio. A ratio can be looked at mathematically as one number or one input over the other one, like a fraction. But when you're dealing with signals that have been turned into logarithms, if you add them together, then you're multiplying. If you subtract one from the other, then you're dividing. So these are connected in a way that the logarithm of one is subtracted from the other one, and therefore you're creating a mathematical division using logarithms. So that's how we get the ratio. Now, just like this circuit required an input current based on the input signal, this one requires a current as well, but this is the reference side of the circuit, so this is just going to be a fixed value, but it needs to be a carefully controlled current. It can't just be some sloppy slapdashed thing. So instead of just having a resistor tied to some voltage, we want it to be more stable than that. So what we have is a constant current source circuit. We take the plus 12 volt power supply rail, which is pretty stable, but it's going through all sorts of traces on the circuit board, and by the time it gets to this set of components, it's probably not completely 12 volts, or it may go up and down a little bit in voltage. You need it to be more stable than that for best results. So we have a Zener diode here, 4.7 volts, and a regular diode. Zener diode's reverse biased, this diode's forward biased, and then through a resistor to ground. So a kind of a classic Zener diode voltage regulator, or voltage reference at least. It's got the 4.7 drop of the Zener plus the 0.6 volt drop of the forward bias diode, so about 5.3 volts. Subtract that from 12 and the rest is dropped across this. That 5.3 volts is placed across these two resistors, a fixed resistor and an adjustable, well, trim potentiometer. This is the decibel reference adjustment trim pot. So you have a stable voltage across this, and you tap off a particular voltage and feed it into the input of this transistor. If you have a transistor configured like this, a PNP with a resistor going to a positive power supply voltage, and then you hold the base at a constant voltage, then the transistor will arrange to have a constant current going through it like this. And that constant current goes in here. So that is the constant reference current going into the reference part of the logarithm circuit. So what we have over here, and this is the output of this overall circuit, this is a DC voltage, just like the signal coming into it was, and it's 3 volts at full scale, but it's negative 3 volts. It's been inverted from a positive 3 volt full scale to a negative 3 volt full scale, and it's also no longer the linear input, it's a logarithmic value. But 3 volts still means full scale on the meter. So we come out of there, and we go through here, and we go into this switch. Again, assuming we're in the dB mode, this switch is already shown in the dB mode. So that 0 to 3 volt signal comes in here, goes around, goes through the resistor, goes through the meter movement, comes back here, loops around, and goes to ground. So it's the same arrangement we had for volts, except that now the meter is connected backwards. The signal is going into its minus side and leaving to ground via its plus side. But that makes sense because when we were in volts, we were dealing with positive voltages and you wanted to connect the plus side of the meter up to that. Here we're dealing with a negative voltage, so we're connecting the minus side of the meter to that and grounding the plus side. But it's still the same scaling, so 3 volts applied will result in 200 microamps, which will result in a full scale, which is what we want and expect. There's one more thing I wanted to say about this circuit, and it's more sensitive to this because of the logarithmic nature of the conversion. This particular configuration is sensitive to temperature. All semiconductor devices, to some degree or another, are sensitive to temperature. Their properties, their effective resistance will change with temperature, and usually it's a negative temperature coefficient. The negative temperature coefficient just means that the internal resistances of the device will decrease as the temperature increases. So one goes up and the other goes down. That's a negative temperature coefficient. In this particular type of circuit, when that happens, it'll be more pronounced in the output than it would be with the other circuits that we've been talking about in this meter. So we need to compensate for that negative temperature coefficient somehow. And this is actually a fairly classic circuit. You can see this in textbooks with only tiny variations. And usually what they want you to do is take these 2 resistors here and make them both ones with a positive temperature coefficient. So when the temperature goes up, the resistance goes up. That's the classic way of doing it, but Heathkit's decided that the only place it really needs to be done, at least to keep the meter within specifications, is just do it with this one resistor here. So that's why I've notated here PTC for positive temperature coefficient on this resistor and this resistor only. Usually, positive temperature coefficient resistors are thermistors, that type of thing, or devices that are used to limit current when temperature gets too high. In this case, Heathkit just calls it a resistor, a special resistor. Looking at the circuit board, this is that special resistor. Kind of looks more like a capacitor here. I can't tell what technology it uses. Some types of more or less regular resistors exhibit some positive temperature coefficient. Some types of film resistors, I don't actually remember off the top of my head which ones do that, but suffice it to say there are different types of resistance devices you can get that have a positive temperature coefficient, and this is one of them. So you don't want to be taking this part out if you ever work on one of these and decide that you put an ohm meter on it and you don't get a reading that's stable, it's moving around with temperature. You think, oh, that's a bad resistor, I'll just yank that out and put in a, a carbon composite or a metal film or a thin film or any kind of resistor you may have laying around that's 1,000 ohms, it won't work properly. This is a special one, and one that's there should probably remain there unless you have the full specifications for what it needs to be to work in this circuit. The only ICs on this whole thing, there's only the 4 of them, and 2 of them are op amps and 2 are really just those transistor packages. The op amps do need power, and IC1 and IC3, that's these two, are powered from the plus and minus 12 volt power rails, and they have local decoupling capacitors or filter capacitors across them, to ground, of course. On the original Heathkit design, these are tantalum capacitors. Whoever had my 5238 before me, and I had already noticed that some capacitors have been replaced because they were more modern types. And indeed, these two are no longer tantalums, they're just regular general purpose aluminum electrolytics, which will work. I don't think there's anything about this design that really requires these to be tantalums to work properly. An op-amp circuit like any of these can have a fair amount of noise or inconsistency of voltage on the power rails unless you're trying to operate the circuit or the op-amp so that it's approaching the power rails with its output. And none of these do. The power rails are far away from where the signal is going, so I'm not actually sure why Heathkit decided to use tantalums on these or not. Tantalums are low leakage and they have other good characteristics, and they're often used for timing circuits where you want to make sure they don't drift with time and so on. But in this situation, I can't think of any reason why you shouldn't replace those tantalums with just a regular electrolytic capacitor. Finally, we also have a dB output jack, and we need to buffer the signal. This signal here, well, I'm sure it's strong enough to drive the meter movement and drive that jack, but you never know what people are going to connect up to these circuits. You could connect something out here that loads this down in a way that throws off the accuracy of the signal reflected on the meter. So it makes sense to buffer it before it goes out to the real world. So we have a circuit that's just like what we've seen before. We have 2 more transistors in that package of 5 matched transistors. And we have a booster output, and we have an inverting amplifier. This inversion compensates for this being a negative signal. So now we have a positive signal, and again, it's 3 volts full scale, so when the meter is at full scale, there's 3 volts on this. And you can connect that again to a chart recorder or some other piece of measuring equipment, whatever you may have. And again, there's feedback. Pretty straightforward. All of these circuits I've been talking about have 2, 3, 4 little disc capacitors scattered around on them for compensation and stability purposes. They have been omitted for clarity. I notate in each things on my sketch which capacitors are not being shown. This circuit is missing 2 capacitors. This one's missing 2. We are missing 1, 2, 3, 4, 5, 6 capacitors here. I think 3 in each half of the circuit. I can't really think of anything else to say about this circuit.